Hello, and welcome to EECS203. This is group B10, and today we will be covering the Monty Hall problem. Our group members are Jared Barber, Mike Ferguson, Tommy Seidel, and Scott Godbold. You can view other videos like this at noatom.com. Here you can see lots of discrete mathematics videos, which should be very helpful for learning more about the subject. First, let's talk about the Monty Hall problem. In it, there are 3 doors, and behind 2 of the doors, there are goats. And behind 1 of the doors, there is a car. For the purposes of this example, we are going to be assuming that you want the car. So you choose one door, but you do not yet open it. Then, the host Monty Hall, out of the other 2 doors that you did not choose, he opens one to reveal a goat. Now you are given the option of switching doors. Do you want to stay in your original door or switch to the new door? Here we need to figure out if switching to the new door increases your probability of getting a car, decreases the probability of getting a car, or does not affect it either way. So, starting off, all 3 doors have equal probability of 1/3. Now, instead of just viewing it as 3 doors, let's try to sort these into buckets. So, the first one, the left-hand bucket, has a 1/3 chance of it being in that bucket, and there's only 1 door. The right-hand bucket has a 2/3 chance of containing the car, but there are 2 doors. So this maintains that each door still has a probability of 1/3, and the probabilities all add up to 1, which is good. Next, Monty Hall opens one of the doors to reveal a goat. So now we know that door 2 has a goat and does not have the car. So now, a common pitfall for this is to think, oh, there are 2 doors. This means that there's now a 50-50 chance. However, when he made the original guess for door number 1, there was a 1/3 chance. So there is still only a 1/3 chance that you are right initially. What happens instead now is that the right-hand bucket still has a 2/3 chance of having it in its set of doors. However, since door number 2 is now disqualified, the probability from that is distributed onto door number 3. This means that while your original one only has a 1/3 chance, door number 3 actually has a 2/3 chance of having the car. So in this case, you should definitely switch, because it will make you much more likely to get the car. So now, it's often easy to understand better if you have an exaggerated sort of example. So, let's do that. So let's increase the number of doors to 100. So, the first door you choose has a 1 in 100 chance, which is not a very good chance. And the other bucket, there has a 99 out of 100 chance of having the car in any of those doors. Now, Monty Hall is nice enough to eliminate 98 doors out of the second bucket, which leaves you with only 2 doors to pick: your original door or the second door, or the door number 100. Since it was so much more probable that you did not get the right answer the first time, that means that it is more probable that the other door is correct. You have to remember that since Monty Hall knows which of them are goats and which one is a car, he can skew the results to only eliminate ones that have goats, which means that it skews the eventual answer to give the one that he can eliminate but does not eliminate, that gives it a much better chance. So that means that your door, while it only has a 1% chance, the door that he leaves remaining is much more likely. It actually now has a 99 out of 100 chance, because it's the conditional probability that you chose the door and he eliminates all the other ones is much lower than the conditional probability of it being one of the 99 doors, and it doesn't have any choice on which ones to choose. Now, this is EECS203, so we can't go and only do the simple solution. We have to go and generalize this and make it more interesting and complicated. So let's do it with an arbitrary number of doors. So n. So when you pick a door, there is a 1 in n probability that it is the car, which makes sense. There is one positive outcome and n possible choices, n possible solutions overall. So the remaining probability is distributed among the unknown doors, which is n minus 1 over n. So the number of doors in that set over all the doors total. So this means that each time the host eliminates a door, the chances get better, distributing the same n minus 1 over n through the rest of the n minus 2 doors. This makes sense because since we talked about it being in a bucket, every time that one is removed from that bucket, and the bucket still has the same probability, the other doors must absorb the probability from that one. So now, let's not only have the doors, let's also add an arbitrary number of prizes. So we have p prizes and n doors. So the probability there's a prize behind any single door is p over n. Again, the number of positive outcomes versus the number of total outcomes. So, the first door that you choose is p over n, which makes sense, as we talked about before. Now, the probability for the other doors, the overall probability for that side, is p over n, which is the probability for any particular door, times n minus 1, which is the number of doors. So you have they have the probability of any individual doors times the number of doors in that bucket, which gives the overall probability that for that entire side. So now let's do it with more doors, as he removes d doors. The probability for all doors that you did not choose is, as we showed before, p times n minus 1 over n. The probability for all doors, the probability for any individual door in that set is p times n minus 1 over n times the quantity n minus 1. This makes sense because you have the probability for all the doors, and there are n minus 1 doors in that set, which means that any individual door will be the entire probability divided by the number of doors. Now, after removing d doors, instead of having just n minus 1, we actually have n minus 1 minus the number of doors that he removed. So that means that the new probability for each individual door that is left will be p times the quantity n minus 1 all over n times the quantity n minus 1 minus d. So that is the general formula for this problem. Now, for those of you who follow diligently, you will be lucky enough to get a brand new shiny car, which is really exciting, so congratulations. But if you didn't, there's still a bright side, as you can still get a goat, and goats are pretty awesome, as you can get delicious cheese and milk, you can use them as an emergency food supply in a pinch, they can traverse rough terrain, which is surprisingly useful in a pretty good number of circumstances, they can help dispose of your excess garbage, and they can take care of your lawn, and much, much more. Well, thank you, and whatever your outcome is, we hope you learned something in discrete mathematics, and we hope you come back and learn more and enjoy learning the subject. Thank you.